Let me present our work of the proof of Spacetime, efficient checking continuous data availability. This is I'm Long Chen from NJIT, and this is a joint work with Giuseppe and Mohammed from Stevens Institute of Technology, and my colleague Qiang Tang, also from NJIT. Okay, let's start. As we all know, outsourced storage has become a common practice for internet applications. Many applications using outsourced storage for backup and data sharing. And even if applications adopt outsourced storage, it can greatly save the cost of many applications. But we pay special care in some cases that when we're using outsourced storage, we need to pay special care. Here I give you a concrete example. Imagine that a hospital stores medical imaging data on the cloud, and surgeons will consult this data during an emergency surgery. So can you imagine that a brief downtime of the cloud server the data not available for a certain amount of time, this will cause a serious medical accident. So this lesson tell us continuous data availability is very crucial. Okay, so we can see from the lesson that for the mission and business critical applications, brief downtime may lead to a serious negative consequence. For example, they will cause loss of productivity, will cause the financial pain of the users, and will damage the business reputation. However, in the real world, there are multiple threats to the continuous availability. For example, the equipment failures, the power outage, and even malicious attacks from hackers. To guarantee the continuous availability, in general, the server we need to devote more. For example, the server needs to keep the more replications of the data. The server needs to devote more hardware and the software components. And also, even the server will involve a more complex administration work. So the conclusion is, continuous availability means a high price. However, in the real world, a dishonest server has the incentive to provide an inferior service to save the cost. For example, the dishonest server will move the data from the high-end equipment to the inferior devices, like this one, and this can save the cost. But the client who has paid a high price must to verify the quality of the storage service. So the client must have the right to verify the continuous data availability. So that means we need some tools and mechanisms to help the client to verify the service, the outsourced storage service. Okay. Besides the verification of the continuous availability, I will introduce another very interesting applications called Decentralized storage market. In the decentralized storage market, the data owner can outsource the data file in the internet, and any party in the internet who wants to provide the service can download the file and store the file for a period of time. And this party will get the reward via the blockchain. So the key point is, in the decentralized storage market, there is no centralized dealer to control the market. To realize these interesting applications, we need a cryptography protocol to help data to verify the service of the server. For example, after the data outsources his file in the internet, and the data owner will initiate a smart contract in the blockchain, maybe in the Ethereum. And also when the server downloads the file, he provides the storage service for a period of time. The server must provide a very succinct proof to the smart contract. The smart contract will verify this proof and give the reward to the server. So the key point is the proof pi must be succinct and the verification must be cheap. This is the requirement that comes from the property of the blockchain. Okay, so for these motivations, this paper we proposed a new cryptography primitive which called Proof of Spacetime. Here we will provide its definitions, we will give constructions, and also we will talk about how to initiate this scheme. First comes to definitions. The basic framework of the POST is very simple. It is interaction between a server and the data owner. The data owner will, first of all, the data owner will store his data in the server. And when the storage period begins, the data owner will send a challenge to the server. And when the storage period ends, the server will give a response to the data owner. But although the framework was simple, to provide a formalized security definition cost more thoughts. Our idea is inspired for the classic primitive called proof of retrievability. The goal of the proof of retrievability is to verify data availability. So the formalized security definition of POR is defined by extractability. And for our case, the proof of storage time, our goal is to verify continuous data availability. So we provide a formalized define called continuous extractability. So what is continuous extractability? It's a game between the adversary and the extractor. The adversary will generate a machine who can always provide a valid POST proof. But we need to guarantee that the data will always store on the machine during the computation period. So how to guarantee that? Our idea is we involve the extractor. The extractor will send a query to the machine, the POST challenge, and also an instruction. The instruction said, okay, you start the POST protocol, and please stop at some time point t. And when the machine stopped at time point t, he will intuitively he will recall all his current state in his memory, right? So to guarantee that the data is indeed stored on the machine, we give back the memory, which records the current state of the machine, give back to the extractor. If the extractor can successfully recover the data from the memory, we can guarantee that the data is indeed stored on the machine at time point t. And since t can be arbitrary time, we can guarantee that the data is continuously available on the machine. Okay, let's come to the construction. First of all, I will show that some naive attempts to show that to provide a POST construction is highly non-trivial. First of all, let's recall the classic protocol which is called proof of retrievability. Proof of retrievability is a challenge response protocol can verify data availability. However, POR can only certify availability at the time a valid proof is processed, only a time point. But if we want to verify the data is available for a time period, a trivial extension can frequently invoke POR. But however, this solution is inefficient in communication and verification because you need to always verify POR, give POR challenges, and verify POR response. And of course, the client should be always online. So maybe someone think about that, whether we can send all the POR challenges in advance. That means at the beginning of the storage period. But in this case, the prover may compute all POR rapidly and discard the data. Another suggestion should be the POR challenges sent in the very end of the storage period. But in this case, the prover could keep the data offline and retrieve them at the last moment. So in the Filecoin white paper, the people proposed an ad hoc solution for this problem. The idea is, first of all, the data owner sends a POR challenge C0 to the server, and the server compute the first POR proof P0. But instead, let the data owner send the next challenge. We derive the next challenge from the hash of the previous the previous POR proof P0. This can be derived by the server itself. We are not involved the data owner. Okay, so the prover will continually compute POR proofs and iteratively execute its procedure. Finally, the server will return all POR challenges, CI and PI. However, this ad-hoc solution has some problems. The first problem is there's no concrete delay guarantee for this solution. That's why even this solution using hash as the random oracle to force the POR to be computed sequentially, but even the POR can be computed sequentially, the malicious server even can finish the computation rapidly and still can discard the data for the last storage period. Also, the verification is inefficient because you need to verify all the POR challenges and proofs. So what's our idea? Our idea, we involve a tool called verifiable delay function. In general, verifiable delay function is a function that everyone to compute the function will cost at least time t. That means even a malicious guy, even with unbounded parallel ability, he cannot get the result within time t. That means a delay is guaranteed. Okay. Also, there is a very succinct proof pi, and using the succinct proof pi, anyone can verify the evaluation of the function. And the verification will not take time, will not cost delay. So, what's our idea? Our first idea is to replace the random oracle hash with VDF. So we guarantee that the POR computed sequentially, and between two POR, there are specific time delay. So why we need specific time delay? We want to guarantee that the data server to check the data once for a while during the whole storage period. So if there is a specific delay, we can guarantee that if we cut the time into every slot, and every POR will be computed in a specific time slot, they will not be rapidly computed at the beginning of the storage period. So this is our warm-up construction, but this construction still has some problem. The first problem is the proof size is too large. Also, the verification is inefficient. So our next idea is we introduce another tool called Trapdoor delay function. The Trapdoor delay function is similar to the VDF, but it's a function will need delay. That means parallel computing cannot accelerate the evaluation of the function. But instead of the succinct proof to verify the evaluation, trapdoor delay function has a trapdoor. That means everyone has a trapdoor can evaluate the function very rapidly. That means without delay. Okay, so let's come to our main construction. Equipped with the trapdoor delay function, we can make the server do the same thing. He sequentially compute POR, and between the POR, there are specific delay time. But to verify the behavior of the server, our idea is to let the data owner to do the same thing. But the data owner will compute sequential POR in the storage phase before he sends challenges. And all the PORs as challenge and proof should be exactly equal to what the server has to compute. The only difference thing is since the data owner have the trapdoor, so there are no delay between two PORs. There's no delay, yeah. So the verification should be simple. We just have to compare the POR computed by the data owner and the POR computed by the server. Okay, since this verification mechanism is simple, we can further aggregate the proof. Our idea is involve hash function. We can just compare the hash value of all the POR computed by the data owner and all the hash value of the POR computed by the server. So the verification is extremely simple. We just compare hash values. Okay, but another question is we want to make the verification to be publicly. So how to make it publicly? we let the data owner to public a tag. The tag is equal to the hash of the hash value of all the PORs computed by himself. So the verification should be let the server to output a hash of the PORs, and the verifier will compute the hash of the PORs and check the hash value whether equal to the tag. Okay, so this verification can be publicly and is extremely cheap, since the verification algorithm only need to check one hash value. Okay, so it can be used in the decentralized storage market. In the decentralized storage market, the data owner will generate the tag in the smart contract, and the prover will give, after store a specific time period, will give a hash value of all his POR he computed. And the verification should be verify the tag whether equal to the hash value, which is extremely cheap. Okay, so the smart contract will, according to the verification result, will give the reward to the server. However, how to initiate these protocols? We can see that we can see that the efficiency of these each procedures. For the verification, we already talked about, is extremely cheap, extremely efficient. But for the proof, since the server need to continuous compute, and their specific delay will in the server side, so that cost is inherent. Okay, so the only left concern is the storing procedure. That means the procedure the data owner put the data on the server. Okay, in our paper we described several techniques to optimize the storing procedure. For example, we adapting hash-based PORs, which is instead of the RSA-based or pairing-based PORs, since the hash symmetric primitives is extremely efficient, it can be used in our settings. Also, the computation of the POR can cause computation of the POR can be optimized by pre-computation, and of course, it can be accelerated by parallel computing. And we believe they have maybe further methods to optimize the storing procedure. Okay. Even with that, we show some benchmark of our storing procedure. From the picture, you can see that if we want to store the data for 1 month, and we want the server to check the data every hour, the storing procedure only takes several minutes. You can from the first line, for 64 megabytes, they will cost maybe 3 or 4 minutes. Okay, in summary, we provide a POST can verify continuous data availability, and our POST also can be realized the decentralized storage market. And then I will talk about a little bit of future work. One of the future work is further optimize the storing procedure, of course, and another thing is in our POST, our construction is stateful. That means since the data owner need to compute POR in his side, previously he sent challenges. So our protocol only supported bounded queries. So the question is whether we can construct a POST to support polynomial queries. And also, our POST is not fully public verifiable. That means the challenges only can be computed by the data owner, but not by the third party. So the left question is maybe we can design a new protocol to achieve public verifiability, and of course, we can imagine more applications. Okay, thank you for your attention.
Thank you very much. So we have time for at least 2 questions. Well, there are no questions. Well, on this note, I think we can wrap up this session. I want to let you know that we need to be very thankful to our speakers for being on time. So let's give them a big hand.